right, guys, we're getting a little deeper here. We're coming close to our factoring. Here they're talking about multiplying monomials, and I'm gonna just jump straight to it. The principle for multiplying monomials is the same principle for multiplying polynomials, right? They only call it monomial because it's one factor times one factor. So those are monomials, and then as it progresses, it becomes polynomials. Here we have a monomial times, two terms, right? So see, they say multiply a polynomial by a monomial. So here we go. We got a one term here, and we got three terms here. So it's a monomial times a polynomial. So it's the same principle. But before we get into this, right, multiplying two polynomials, that's where you see we have a group with two terms times a group of three terms. So polynomial times polynomial. And then you're going to have the one where you're going to be multiplying binomials. That means two terms by two terms. Where is that? Oh, the book didn't get into that. Oh my goodness. Well, maybe I skipped it, but here's an example. Here is a binomial, two term times another two term, and they usually call it using the FOIL method. I know you guys are here it is, multiplying two binomials. The product of two binomials can be found using the FOIL method. Scratch that. I'm not big on the FOIL method, but what it is that the FOIL method is saying you multiply the first term by the first, then the first by the second, then the second term by the first, and the second by the second. And they're like all fancy, first term, outer term. Who wants to remember all of that? This is what I'll tell you you must remember. And I'm going to get in depth with it. Just remember that whenever you're multiplying terms, when your terms become factors and they have to be multiplied, the distributive property is what really comes into play. Even though the distributive property is talking about a monomial times a polynomial, it's the same principle where you're going to be multiplying one term times a group of term and adding the rest. Well, you know the rest. I'll get into it. However, before we get deep into multiplying and dividing polynomials, I want to teach you guys the rules of exponents, or I should say reteach you. Also, you actually have this in the first set of notes that I provided to you at the beginning of the semester. So a little slogan when it comes to the rules of exponents or using exponents is when in doubt, expand. Now, here's what I mean by that. So the first rule of exponent here, first of all, let's understand what an exponent is or revisit it. We have a base and an exponent or a power, right? People call this a power. Okay, right? And what that power is telling you, or that exponent is telling you, is an exponent is really the number of factors of the base that you have. So if my base is 2 and my power is 4, right? Or my base is 2 and my exponent is 4, this exponent is basically saying I have 4. You guys see my 4? I have 4 factors of my base 2. So I have, remember, factors, multiplication and division. In this case, it's clearly a multiplication. So I have 2 times 2 times 2 times 2, which when you find these product, you'll get 16. All right. So it's just an example of what an exponent actually is. Now, here are some rules to remember. So basically, they're saying if you have the same power, now these rule only applies to factors, not terms. Right? These rules of exponent only applies to factors. Factors, not terms. Okay? Factors and not terms, right? So here we go. If we are multiplying two bases that are the same, right? Two exponentials with the same base, we add their powers, right? And I think we said this before, so this should be revision, but it's okay. So here we go. If you're seeing it for the first time or it feels like brand new to you, it's fine. So x to the n times x to the m is the same as saying x to the n plus m. So for example, if I have x squared times x cubed, is me saying x to the 2 plus 3 or x5. Now here the rule comes in, when in doubt, expand. If we were in class, this would have been an exciting time for quiz. Did I do this with you guys before? All right. Anyway, if I did, it's revision, right? So when in doubt, expand. So let's say you don't have this rule. What we do know is that the exponent tells you how many factors of the base you have. So for x squared, where am I? X squared, I have 2 factors of x, 1, 2. And for x cubed, I have another 3 factors, right? 1, 2, 3. So I have a total of 1, 2, 3, 4, 5 factors, right? So that's x5. So that's if we wanted to, when in doubt, expand, right? What these rules help for is if you had x to the 100 times x to the 550, you don't want to expand x 100 times, then expand x 150 times. So those rule comes in handy where you would be expanding. So let me just write that. So x 100 times x to the 550. You don't want to be expanding these two. So that's why it's good to know the rules, the addition rule of powers when multiplying the same bases. So this would actually be x to the 100 plus 550, which is 650, x to the 650. So that's how the rule helps. However, you shouldn't be seeing big exponents like that. So again, when in doubt, you could still apply the rule expand. All right, so that's the addition rule of exponential factors with the same base. Now, what happens when we're dividing? You guessed it, or you see it. When we're dividing the same bases, we subtract. Again, here's an example. If we have x to the 4th divided by x squared is x to the 4 minus 2, which is x squared. And again, when in doubt, expand. Here I expanded x to the 4 and I expanded x squared. You see, when I expanded them, what happened? They cancel out common factors, and what am I left with? X squared remaining. So that's where the principle of subtracting powers came into being. That's a proof. So now we have another power of when we have one power raised to another power. So if we have a power raised to another power, we multiply those powers, right? So x to the n raised to the m is the same as saying x to the nm. So if we have x cubed raised to the 2nd power is the same as saying x to the, 3 times 2, 2 times 3. Multiplication is commutative, shouldn't matter. So this is x to the 6th power. Again, the rule of when in doubt, expand still applies here. Here we have 2 factors of x cubed, right? That's what our power is saying, 2 factors of x cubed. So I have 1 factor of x cubed here, 1 factor of x cubed here. And within these parentheses, I can expand my x cubed, 1, 2, 3. Expand my other x cubed, 1, 2, 3. And now I have 1, 2, 3, 4, 5, 6 factors of x. Hence the proof. And like I said, these rules come in handy if we have big powers that we have to simplify or evaluate. All right. So and otherwise than that, if the powers is small enough and you can't remember, just expand it and you'll see. All right, good. So the other rule says any base raised to a 0 power is 1. Any base raised to a 0 power, it doesn't matter if it's a smiley face, it could be like a xy squared z to the 100. As long as you raise this to the 0 power, it's 1, right? Why is that? It's actually a division concept. So let's take a look at when do factors become 1? When we divide the same factor. Anything divided by itself is the same as 1. Now, if we have x squared minus divided by x squared, it's the same as saying x to the 2nd minus 2nd, right? 2 minus 2, which is 0. And the rule says anything to the 0 power is 1. And that's proved by a division concept because this x to the 0 simply means that x had a power, or x was a base that was divided by itself. It had a power that was the same. So they cancel out each other. And when factors cancel out each other, it doesn't disappear. They're not terms. When terms cancel out each other, you get 0. They have opposite sign, you get 0. However, when factors cancel out each other, it's 1. So remember, any factor divided by itself is 1. So example, look, we got 2 divided 2 is 1. And this is because we could say 2 to the 1st power over 2 to the 1st power is 2 minus 2 to the 1 minus 1, which is 2 to the 0, which is 1. That's where that concept comes in. And last but not least, there's a cardinal rule that you cannot leave your exponential in a negative form. So whenever you have a negative power, it's actually the reciprocal of that base raised to the positive power, right? So you see, this is x to the negative n. That's a whole number. Its reciprocal is 1 over x. So same, if I had 1 over x to the negative n, the reciprocal would be the reverse. It would be x to the n. All right? So that's what reciprocal means, the reverse. You're going to see this at least on a test, I believe. All right? So here's an example. X to the negative 2 is the same as saying 1 over x squared. And where did that concept come from? That also come from a division concept. But in this case, what's happening is that with your division concept, you know you have to subtract power. It means the denominator, the exponent in the denominator was greater than the numerator, right? Now, if I expand these to x squared, x4, if I expanded them, you see what I'm left with? This cancels out. We're left with 1, not 0. We're dealing with factors and 2 factors of x remaining. So that's 1 over x squared. Because remember the rule says when dividing same bases, you subtract. So if I subtracted 2 and from 4, all right, I'm going to be left with a negative 2. Positive 2 minus 4. Subtract, keep the sign of the greater magnitude. It's left with negative 2. But my answer cannot be a negative power. Just like how you have to reduce fractions, you cannot have negative powers. You must convert it into a positive, and that rule says reciprocate. All right? So again, when multiplying, same base, add powers. When dividing, subtract powers. When raise a power to a power, multiply powers. Anything to the 0 power is 1, and a negative power is its reciprocal raised to the positive power. All right, now we're going to get into multiplication of polynomials, period.